Well, welcome back. What we're going to do now is look into the energetics related to solution formation. In our previous videos, we've looked at intermolecular forces and how that relates to the interaction of a molecule and another molecule of the same substance and the attractions between them. And so now what we're going to do is we're going to look at what happens when we make a solution. And again, to remind us, when we talk about a solution, we can think of kind of three main things that we want to focus on or understand in the back of our minds when we think about a solution. We think about the fact that we have a solution, which is a homogeneous mixture. In addition to that, within each solution, we have the solvent and we have the solute. And we have these two components of a solution. The solvent, we typically think of as the major component, or also we would also consider that to be whatever is causing something else to be dissolved. And then when we think about the solute is typically our minor component, and we can also think about it as what is being dissolved into our solvent. So now again, we're making a solution. What happens to the molecules? How do they interact when we make a solution? So we're going to do this by looking at three distinct molecules. We got hexane, water, and isopropanol. And we're going to look at them individually as pure substances. And then we're going to also connect to the idea of what happens when we mix these things together. How do those molecules interact? And whether or not they will be miscible, and what we mean by miscible. Okay, so now as we have this, let's go ahead and start and reflect back on what we know from our previous material and thinking about the interaction of just hexane and hexane molecules, water and water molecules, and isopropanol molecules. So why don't you go ahead and pause the video, and why don't you list all of the intermolecular force attractions present between hexane, water, and isopropanol as pure substances. So now as we did that, hopefully we were able to identify that every single one of these substances have the ability to undergo London dispersion force attractions, right? Because we can have the movement of our electrons within a molecule. Now our hexane molecule is a non-polar molecule. We look at it and we see it's symmetrical, and because it's symmetrical, there's no side of the molecule that has a greater electronegativity, a greater draw on the electrons, and so we don't have any these poles present, positive and negative poles, so it's a non-polar molecule. So it would not have the ability to undergo dipole-dipole interactions or hydrogen bonding because there's no hydrogen directly bonded to an oxygen, nitrogen, or fluorine. Then we go and we look at water and isopropanol. Those are both polar molecules, so therefore they also have dipole-dipole attractions in addition to the London dispersion force attractions. And then we also see, do they have hydrogen directly bonded to oxygen, nitrogen, and fluorine? And we look at water and our isopropanol, both of them have that oxygen directly bonded to our hydrogen. So we see that they both have the ability to do hydrogen bonding. And so within the possible interactions that these molecules can have, the strongest interactions that hexane can have are London dispersion force attractions. We would have the strongest interactions between water and isopropanol and isopropanol would be hydrogen bonding. And so then again, this is just looking at these pure substances. Now we're not going to try and identify whether hexane is miscible with hexane. Hexane will mix. It's something that it's going to happen if we have the same substance. So now what we want to do is we now have three new sets of molecule A and molecule B, or 1 or 2, and thinking about how these molecules can interact with each other. And kind of one thing to be aware of as we're thinking about this is that for there to be kind of relatively strong interactions between two different molecules, so that would be water and isopropanol, or hexane and water, hexane and isopropanol, there must be some similar type of interaction. So maybe they're both London dispersion force attractions is the strongest that they can have, or dipole-dipole attractions is the strongest they can have. And so that's the kind of interactions that we would have between them. So now if we look at a water molecule and an isopropanol molecule, those two molecules have the ability to undergo London dispersion force attractions. Again, that's because every molecule has electrons that can shift around, causing these instantaneous dipoles. With water and isopropanol, though, these are both polar molecules. And so that would mean they both also have the ability to undergo dipole-dipole attractions. In addition to that, they both have an oxygen directly bonded to hydrogen. So they both have the ability to have hydrogen bonding. And so now we'd see, because that's the strongest attraction that either one could have separate, but also together in this mixture, that would be the same as the strongest interactions that those molecules would have when we make this mixture together. And then we're going to make an observation in a second after we look at the other possible interactions that hexane and water can have, or hexane and isopropanol, and think about this idea of whether they're miscible or immiscible. So we go down to hexane and water. Hexane and water, we see that really the only overlap of interactions that they have is London dispersion force attractions. We see that that's the strongest attraction that hexane have, and that is one of the interactions that water has the ability to do. And so that would mean the strongest kind of interaction that these two molecules can have is London dispersion force attractions. What we're going to see is maybe we're going to compare that back to the idea of whether these things will mix based upon the interactions that water has by itself or hexane molecules have by themselves. Then we move on and we look at hexane and isopropanol. Hexane is also a nonpolar molecule. Isopropanol is polar. However, the only overlap they would have in intermolecular force attractions, again, would be our London dispersion force attractions. And so that would mean the strongest interaction that those molecules could really have are these London dispersion force attractions. And so then what we want to do is we want to answer the question, will these substances mix or will they not mix? And in order for two liquids to mix, we would say, yes, if they do mix, we would consider them as being miscible. And so we can think about something that does mix would be miscible. So if I took those two liquids together, they would look at like a mixture. We couldn't identify them together. We can also consider them to be two different liquids being immiscible. And that means they do not mix. So what we would observe if we put these two things into a beaker is that we would get kind of two distinct layers where you would see one substance and another substance. Think about this with salad dressing. You would see maybe olive oil and vinegar. Those two things do not mix. They would be considered to be immiscible. Okay, so we would say, well, at a molecular level, what's going to affect whether something is miscible or not miscible? And what we want to do is we want to compare the kinds of interactions that those molecules can have together versus separately as individual pure substances. And so what we notice, for example, with water and isopropanol, they have the ability to undergo hydrogen bonding simply with a water-water molecule or isopropanol-isopropanol molecule. However, when we mix them together, they still have the ability to undergo hydrogen bonding. And so what we notice is that they still have the same type of intermolecular force attractions, or at least similar. In this case, we notice for our hydrogen bonding. Because of that, we would notice that if we do mix these together, that they would be miscible. So we make this observation that if there is similar types of interactions between the separate substances, and then those substances mix together, we're going to see that those two liquids will mix together. Whereas maybe we would look at hexane and water. With hexane and water, we would also notice that we would have London dispersion force attractions. It's the strongest thing that can happen between those. But then we compare that back to our original types of attractions they can have separate. And we see here that our London dispersion force attractions in hexane, hydrogen bonding, and water. And now if I were to mix those together, effectively our water molecules would have to separate from other water molecules that they were hanging out with. And now they're going to have to hang out with some hexane molecules and interact them with very weak attractions. And because of that, we would notice that these two would be immiscible, or they would not mix. So again, this would be like that olive oil and vinegar example where we see those two substances actually don't mix. We'd see two distinct layers. We go and we look at hexane and isopropanol. Once you go ahead and pause the video and predict whether you think hexane and isopropanol would be miscible or immiscible. So as we had a chance to predict whether we would say that isopropanol and hexane would mix or not, whether it be immiscible or miscible, we noticed we would compare the original types of interactions that they would have, which would be hydrogen bonding for isopropanol. Hexane would only have London dispersion force attractions, and we see those are so different that we would likely predict that they would be immiscible. Now, if we go back up to, and I put under there this idea of that to be slightly miscible, or as we think about them being mixed, and that's because we notice our isopropanol also has this kind of portion of our molecule that looks very similar to our hexane molecule. And so we see, because we really only have this kind of polar section of where we have hydrogen bonding, but we also have this non-polar section where we have just carbons and hydrogens like our hexane molecule, that we would see that there would also be a similarity within that, and there would be some kind of interactions, but obviously not the same that we would see between water and isopropanol, because both of those also have the ability to undergo hydrogen bonding. So as we see that, we have the ability to maybe make this observation that the more similar they are or the more dissimilar they are, that's going to tell us whether those things would be more miscible or less miscible based upon the types of interactions that they can have. And so if we want to go ahead and generalize this idea into what causes certain substances to mix or not to mix, that brings us to this very kind of familiar phrasing that like dissolves like. Now, what do we mean by that when we say like dissolves like? That we can effectively distill that down to the fact that similar types of molecules will dissolve or mix with other molecules of the same or similar intermolecular force strength. So we look, in fact, do both of those molecules have dipole-dipole attractions? And they're probably going to be fairly attracted to each other. Or do those molecules only have London dispersion force attractions? Maybe something like hexane with butane, and those two substances are both nonpolar molecules, and so therefore they would mix with each other. And so we see this when we're trying to generalize this, we want to think, let's look at the types of intermolecular force attractions those molecules can have, and when we mix them together, how is that going to change those types of attractions? Are they going to have around the same strength? Are we going to still have hydrogen bonding like with our isopropanol and water? Or is it going to be so different like hexane and water, where we have this really small polar hydrogen bonding water to this larger nonpolar hexane molecule? And those two things are not going to mix with each other because they're so different in the types of attractions that they would have, whether in the pure substance to that mixture. And so now that we have this generalization of whether something will mix or not, then we want to think about, well, what happens when we do mix these substances? What changes the overall strength of attractions between those molecules separate or together? And so for us to investigate that now, what we want to do is we want to think more fully into, well, what happens if we have a different type of solute? Instead of a molecular substance as a liquid, another molecular substance as a liquid, what happens if we take a solid and dissolve it into a liquid? And so now again, here we have an ionic compound, one we're fairly familiar with, sodium chloride, table salt. And let's say we add it into liquid water, isopropanol, and hexane. And what we want to look at is and see what kinds of attractions are present now between maybe a water molecule and sodium ions and chlorides ions, and isopropanol and sodium ions and chloride ions, etc. And so let's first investigate what happens when we take sodium and chloride and we put them into water. And so now here we have our sodium chloride ions. We can kind of think of this as continuing to go on and on and on into our solid structure. And again, this would be, if I took a chunk of sodium chloride and I put it into water, that's what it would look like before it actually dissolved, if it does dissolve. And so now we'd have these water molecules, and they're going to come and interact with maybe our sodium and our chloride ions. So maybe let's first start by looking at our sodium ions. Our sodium ions are positively charged ions. And here we have a water molecule where we know one side is negative and one side is positive, right? Our oxygen's more electronegative, our hydrogen's less electronegative. It makes that oxygen side of the molecule negative. And so then when our water molecule comes, the oxygen side is going to face our sodium ion because it's going to want to interact with it. And we can think of it as coming in and kind of grabbing onto that sodium ion, and it's going to pull it out. And now as we have our sodium ion now, as this kind of lone sodium positively charged atom, now it's going to be surrounded by a bunch of water molecules. And we could see here, if we have our water molecule, we're going to have all of these water molecules in kind of this semi-organized fashion where all of those water molecules are facing in a specific orientation, where the oxygen is facing the sodium ion and the hydrogen is facing away from it. And that's because we have this negative charge, again, on our oxygen and this partially positive charge on our hydrogen. So what we're doing is we're forming these attractions between this molecule and this ion, and this would be an intermolecular force attraction. Now, what kind of intermolecular force attraction is this? It's not something that we can think about maybe as a pure substance, because now we have an ion and we interacting with the dipole of a molecular substance, in this case, our water molecule. And so this is what we would call an ion dipole intermolecular force attraction. We have this positive ion interacting with the negative section of our polar water molecule. And so then it's going to cause this interaction to occur between those two substances. And so we say, well, would that be stronger or weaker than maybe a hydrogen bond? And we think we have a fully +1 charge ion interacting with this partially negative charge oxygen atom. That's going to be a fairly strong attraction, because when we first introduced intermolecular force attractions, the greater the magnitude of our charges, the stronger those attractions. And so now we have this kind of fully +1 charge interacting with this partially negative oxygen charge, maybe of something in -0.5. That's going to be a stronger attraction than a -0.5 attraction with a +0.5 attraction. And so because of that, our ion dipole attractions are actually stronger than hydrogen bonding. And so now what we've done is we've allowed our water molecules to interact with our sodium or chloride ions and give us a stronger attraction than we would have seen of just those water molecules by themselves. And so now what we've done is we've developed the ability to increase the strength of our attractions, and because of that, we would notice that this solid would dissolve. And again, that's because we have this polar molecule that can interact with our sodium ion. So now what I want you to do is I want you to think about the same idea of our isopropanol and our sodium and our chloride ions. Why don't you go ahead and draw out, if we had a chloride ion, what would it look like for our isopropanol molecules to surround that chloride ion? And you want to think, are they going to be oriented in a certain way, or will they just be haphazardly oriented around our chloride ion? And think about what the structure of our isopropanol molecule looks like, and draw what it would look like for the interactions that we'd have between our chloride ion and the isopropanol molecule. So why don't you go ahead and pause the video now and draw out what you think that structure would look like. So now hopefully we had a chance to draw out what we think those types of interactions would be. And again, we have this polar molecule, but not as polar as water, of isopropanol interacting with the negative ion of our chloride ion. And so hopefully what we were able to see is that kind of this side of our molecule where we have the positively charged kind of hydrogens and carbons, because of the fact that our oxygen's kind of pulling our electrons away from that side. That partial positive charge is going to interact with the negative charge of our chloride ion, and that right there would be our ion dipole attractions. Again, we have an ion, we have a polar molecule, the dipole of our isopropanol interacting with the chloride ion. Now again, would this be as strong of an ion dipole attraction as the water molecule? No, because this is where we have a weaker dipole present in our isopropanol. And so again, we have to think the magnitude of our charge is going to affect the strength of those attractions. And so we'd have stronger attractions between the water and sodium and chloride versus the isopropanol and sodium and chloride. Now, again, we have these fairly strong attractions though. And so we would also see that we would have our sodium chloride dissolve in isopropanol as well. So now that brings us to our nonpolar hexane molecule and our ions, our sodium and our chloride ions. Now we think, are we going to have ion dipole intermolecular force attractions between our sodium and our chloride ions? Well, our hexane molecule is nonpolar, meaning there is no set dipole present on that nonpolar molecule. There's no one side of the molecule that's always negative and one side of the molecule that's always positive. And so because of that, because there is no dipole, that means that we don't have the ability to have this ion dipole attraction. And so effectively what we have is this idea of this ion kind of pulling on the electrons, inducing a dipole, but that's not really going to be that strong of attraction. And so if we have, for example, our chloride ion here, and then we have our hexane molecule, and we think of it kind of coming close to this chloride ion, it's going to kind of push the electrons maybe away from the chloride ion. And what that's going to do is give us this kind of partial positive, partial negative. And what we've done here is we've induced or caused a dipole in our isopropanol, or excuse me, our hexane molecule. Now, this is not a very strong attraction because this dipole would not actually be present there unless it came close to this chloride ion. And so when we think about these things dissolving, these are not very similar, right? We don't have a charge, a positive and negative charge present on two substances that's always there, and those things are interacting like we have with our ion dipole attractions. Here we have these very weak ion-induced dipole attractions, and because of that, that sodium chloride that I would take and put into hexane, it would not dissolve. So what would that look like? We'd have a beaker containing our hexane, and then we would just have a bunch of sodium chloride sitting on the bottom. It would look like something being insoluble, right? It's not going to dissolve inside of that substance. And so now what we've done is we've thought about types of solutions that we can form. A liquid dissolving into a liquid, whether it be miscible, think of that as just like being, whether it's soluble. And then we also have the ability to think about a solid dissolving into a liquid. And that's dealing with this idea of whether it's soluble or not. Like, will it dissolve? And again, it has everything to do with, are they similar type of attractions that we get present in the mixture of our solution versus those substances together?